We are continuing the last day, the science day of the AI journey. I'd like to remind you that today we are discussing science. We are going to have Alexander Panov. Trained neural network models in robotics are increasingly more often used to generate both high-level behavioral plans and very simple low-level actions. The use of pre-built demonstrations to pre-train such models faces the problem of low generalizability. What are basic behavioral models? What are their basic properties? We'll find out from the presentation of Alexander Panov. A round of applause. A PhD in physics and mathematics, director of the Cognitive AI Systems Lab at AIJ, the director of the Center for Cognitive Modeling, MIPT, Alexander Panov, Basic Behavioral Models in Robotics. Right. Hi, everyone. Welcome you all on the AI Journey conference. We're going to talk about robotics. Quite a lot has been said about the AGI, about what we need to achieve AGI. I am from those researchers who think that it will take us some time to move to the AGI, not 1 year, not 2 years, and during that time we will have to go through this simplified AI, so to speak, something that we need to implement in the robotic devices, something that has to interact with the world and demonstrate its cognitive capabilities, and something that has to be in the physical world, present in the physical world, not virtual, and demonstrate its thinking abilities. Right, so what is the foundation of the learning approaches? Learning from demonstrations, that's the base. We'll look at a couple of examples of foundation behavior models. We'll talk about multi-robot learning. We'll talk about how can you build a team of robots. Let's start with the learnable approaches. Robots will not be able to replace us. They should not do that, but we need to leverage their capabilities to empower ourselves and to resolve new tasks. And these are the situations where robots can augment human capabilities and go to an absolutely new level of various tasks. Construction, for example, I dream to build a detached house or make a renovation at home with a robot, and I would help this robot to do the work. Collaborative robotics is one of the major trends for this year and for the years to come. If you look at this slide, we can see this diagram in terms of the number of robots that we're using right now and the videos that we see on YouTube every day with robots. In 2000s, more and more robots were manipulating robots that were working in these static, determined conditions at conveyor lines, in the factories. Now we see more robots working in these same conditions that we work in the human-oriented environment. In the environment that is comfortable for the humans, not for the robots. And there are more and more robots like that. And the most important thing is that these robots are becoming cheaper. Only large corporations were able to afford a robot. Now, any household can buy a small vacuum cleaning robot and use it. They have to become more universal and more mobile, of course, and to make these robots more universal, we have to use the advanced AI approaches. There are two approaches: the adaptive learning model using reinforcement learning. This is one of the key approaches that around 7 years ago put the robotics development in the new era. Now we can create a reward function that would built this reinforcement learning model. Second is something that the robot connects with the words when it tries to understand what we want to do. And these are the LLM, the language models. 2 years ago, language models became this disruption that helped the robotics to go to an even new level, where we see the robots that are not just falling all the time or switching off randomly, but those who work with us and live with us. In robotics, there are two areas. First is end-to-end models, is when we have a very large neural network that will give us a set of actions that the robots will perform in this or that environment. But these end-to-end models, for some reason, do not work properly. The specifics and of the physical world is pretty challenging. So I think that the modal architecture is going to remain the most popular one. This means that we build a robot from a number of components. So if you look at the robot on the picture, this is a multi-agent system that builds a common control system for the robot. Every component is responsible for a separate part, for the concept, for giving the information about what is happening around the robot. One is responsible for planning, or the other one for training, another one building the map. And this multi-agent system will develop in the future. This is the future of all robotic systems. STRL, by the way, one of the examples, one of the systems that we test on different robots together with the colleagues from MIPT. That's the robot going on in the Technical and Physical University. There are many components in these robots that are learnable and cannot be trained. And that's important because one agent have to train and to get knowledge or get pre-trained, and others can work based on the classical rules with model predictive controls as one of the approaches. And the example of our work today is what we presented at ICRA Robotics conference. It was the only Russian work at the conference. We said that the model predictive control can be injected with a special function called the function of the potential that shows how the robots go through the barriers, through the obstacles. Usually, I mean, the obstacle problem has been resolved for like 30 years, and when we do that, we need to put obstacles analytically. But if we build a map with the CV methods, this is the map that is not even because there are some obstacles that are too complicated. But if we train a neural network that will tell us that, okay, like there might be some obstacle there, it might work. And this is one of the most important results that was well received at the conference. We're going to talk more about the fundamental, the basic models, and of course we know that when we talk about the basic models in language systems, it is all based on huge volume of data that are not labeled. So the basic fundamental models appeared when we were able to extract something from these data, from text, from the images. So we have a huge volume of data, and we were able, without some special labeling, to build this model of the world, well, a so-called model of the world. But anyway, we were able to learn something about this data, and we were able to get this huge memory, let's say transformer model, to resolve this or that task. For example, we wanted to resolve the task of developing a strategy. And this is the basic model. But of course, for robotics, for the behavior data are demonstrations. So it's text for language models. For multimodal, these are text and images. For behavioral models, it's demonstration and doing some task. If we look at this slide, that is very characteristics. If we put all information for text models in tokens, it will be 15 trillion tokens. If we talk about images, it's 6 billion tokens. Videos, that's more expensive. It's 2.6 billion tokens. If we're talking about the robots, the actions that are needed, it's like 2.4 million tokens. Can you believe that? And if we're using the same architecture, transformer architecture, if it trained properly on these 2.4 million tokens, it is hard to expect it to train well on 1 million tokens. So we have two options here. Use something about transformers or try to modify them. The other one is to take data from some other places. That's a very good approach. The first thing, how to use data properly. You don't have to have a lot of them when you have a good algorithm. Serial, that's a pretty popular robotic algorithm. A practical task, you need to insert this thing in this hole, and it's very important for the engineering, because when we develop manipulating robots, it's very important for us to be able to, insert this thing here. And we used some data to pre-train our model, and if we organize not even the algorithm properly, but the sampling of the episodes, and we will complete an episode at any given moment in the right time without using the tokens that we lack severely, we can retrain a robot with real data in 20, 30, or 40 iterations max. So we can build the pipeline of the work of the robots in real environments, and we don't need a lot of data for that. But that's a pretty useless algorithm, because it cannot really do anything else apart from inserting these things here. But that's a good example, published in the library, it's been used quite actively. Now, multitask pre-training, an example of a paper that I really like, the control transformer paper, shows that we can train a model without giving an award. So we don't give an agent the goal, the task. We don't set the task. The agent just sees some actions that are being done, and it then develops the causal effect. And then after that, we train it to resolve a specific task. So we add MLP layers that are responsible for training the transformer for specific tasks. And here it shows that this is how we can receive a basic model with that was trained on the same tasks. We have then similar tasks inputted, and the transformer is playing a role of the fundamental basic model. This is a good example of the fact that transformer model can be used differently from the classical ML tasks. One of the papers that I'm going to talk about today is deeper modification of transformer architecture. It's called recurrent action transformer with memory, RATE. We suggested to expand the context for language models. If we are going to use special tokens that describe not the information but the information from previous tokens, we will say that this is memory tokens, and we will thus understand what information is important, and we'll put information from one stage to the next one. But for reinforcement learning in robotics, we need an additional module here. We called it a specialized memory module. It's here at this transformer part that is highlighted blue. It helps us to map the tokens of memory for each other, with each other. And this is how you can show the efficiency of this architecture compared with the classical transformer architecture where you need memory. That's a great example here, because the robot here is playing that kind of a hide and seek, right? The robot has to remember where the ball is hidden. And this approach works very well. A couple of words about a very popular architecture and approach in robotics is diffusion strategies. We do not have to generate actions step by step, you know. Diffusion model has been around for a while, and we can generate the optimal trajectory on the go, immediately, skipping some steps. It's like we generate a picture from the scratch, right? And for that, we need a diffusion process. So we have to understand how to get one trajectory from a set of trajectories. There should be a reward function, obviously. But this really fits well with the explanation of the diffusion process. And yes, it shows that you can do that. You can generate such trajectory, and quite a lot of papers that explain that method. One of them is used in robotics, diffusion policy. The idea here is that we're not going to generate trajectory, we're going to work in the environment of potential and the gradients of this potential. And the potentials are responsible for the actions of the in the environment where the robot works in. And here the classical diffusion process can be replaced with a process that we train with transformer. So this is how we give these trajectories that generate from noise not to be local, but we can make them long to make this trajectory working. Now, there are some limitations to this approach. We can work with diffusions, but locally. It's very hard to reason them for a text, for example. So it's hard for them it's hard to make them multimodal. I liked one of the papers on the IRIS conference this year that says that maybe we should work not in the flow matching, not in diffusion, but to do the flow matching. And the robot state resides on the Riemannian manifold. Now we can encode high-dimensional multimodal distributions more efficiently, and this is where you can make diffusion process, but actually flow matching instead of diffusion. This is one of the trends that I think next year is going to leverage these methods for more complicated tasks. Let's go to a more classical options of the use of foundation models. I'm going to give a reference to the article that says that we're going to work not with the basic models, but with the basic agents. Now, the paradigm of the basic agents in robotics is something that is close to our hearts. Working with an environment, we get a basic foundational model and use it for some tasks. What should they be? First, it should have a few short attributes. By training on a couple of examples, it should show you the strategy of resolving another task. Secondly, it should have a fine-tune attribute. So fine-tune is where we enter more and more data, and this is where we need to change the weights of the model so it can resolve new tasks.
These are the two main properties of robotics. They are hard to implement, and as I said, one of the barriers is data and the way we are coding the architecture. With data, an important thing, how can we overcome it? It's through generation of synthetic tasks, synthetic data, and creating a closed loop. We start with a small array of data. RoboCat is one of the interesting publications on this. One of the good examples, we are performing tasks, training to perform the tasks from the demonstrations. Then we add 2 or 3 examples of a new task in a simulator. The robot uses these examples to get fine-tuned with the synthetic data generated in the simulator. Then we close the loop, we add more data, and in the simulator we are increasing the amount of data. We no longer need expensive demonstrations where a human would perform this task. This is a very promising area in robotics, synthetic simulators, where we can generate data for different problems. They create an environment where we can generate data without which we could not train foundation models. This is how a foundation model looks. Once we have solved these problems, OpenVLA is one of my favorite architectures. It's pretty standard. All of the main foundation models with the transformer approach work approximately like this. We have a pre-trained core. It can be a language model or a multimodal model. We need to adapt it to work with other modalities, with images, for example, with depth. These adapters need to be pre-trained. For example, we're using a video clip or we're using some other options that transfer us into a unified latent space. These models called VLA are very similar to the traditional models which work with multiple modalities, but as the output they do not generate a video or an image. It's just one of the available tokens. This output simplicity unfortunately adds complexity elsewhere. If the input and output are pretty much the same, we have text as input and text as output, that's one thing, that's pretty simple. But once we make output more peculiar, more specific, we need other methods of regularization, because we need to stabilize the whole process of training. For example, do chunking with a sequence of actions. But that's pretty much how these architectures work. I'm going to give you some other examples very, very briefly. The examples of what we have been doing in our team for foundation models, but not for universal tasks, but tasks related to navigation. So this is a foundation models for navigation using landmarks. We have an image, a semantic map, and a labeling of depth, and the robot must be able to use examples of different rooms or environments to navigate in a new environment with new information, and it needs to do this efficiently. So it needs to extrapolate existing attributes to new maps. We showed how you can do this effectively, and we are showing that the foundation model does not have to be unified. It can consist of different chunks of different modules, each module responsible for a specific task, getting to the target, for example, or exploring the environment, or moving from one landmark point to another across the rooms. The development of this approach was related to the question, why do we need these skills to be trainable? Let's add some good classic skill. And as a result, we got the skill fusion architecture. It enabled us to win the habitat competition, the best-known competition in the world of navigational robotics. And essentially, this is showing that foundation architecture, behavioral architecture, can be modular. And these modules can interact with each other. Simulation with fine-tuning models plays a very big role, as opposed to large language models, for example. This is an example of fine-tuning a model that was working in the text-to-image mode, answering questions based on an image. And we showed that we do not have to disrupt any basic attributes of the model. It can still generate its traditional outputs, but it can also work with a simulator. We're not violating its basic principles. And another important slide, most multimodal problems solved in robotics with the foundation models give us a new modality, for example, an instruction only at the beginning. There are no problems where we are building a dialogue in synthetic environments. This is when we give an instruction, and then at some point we say, no, you're doing something wrong, you need to correct yourself. Or this is the middle of an episode, let's tackle another task, a completely new one. This means we have environments where we can interact with robots One of the biggest projects of this year that we did is developing this environment, this framework called Igor, that enables multimodal reinforcement learning. We can insert a text modality at any point within an episode, and projects like this are very important for robotics. This is an example of our platformer multimodal architecture. We are developing it, and its biggest characteristic is that it needs to be fine-tunable in a simulator. Most models that I showed unfortunately can't do this. This diagram shows in yellow that we were fine-tuning the model in an environment. It was trained initially on other problems, and so it gets fine-tuned online much faster. And the support online only works when we are adding some function to the architecture, such as goal criticism. And now a couple of words about multi-agent systems, another important domain for robotics. In robotics, it's hard to handle one robot, and when you add more, it becomes increasingly more challenging. But robots are becoming more and more reliable, and the next step is interaction between robots and their interaction with the human being. Multi-agent reinforcement learning is the biggest tool that we can use to solve these problems. Our team is one of the leading teams building multi-agent approaches in RR. We are solving the classic navigation problem for several robots so that in the environment of a warehouse they could build their path, they could find their paths without collision. We have built a benchmark called Spalina. 20 to 30 classic algorithms. We're showing how to measure them correctly, because in multi-agent RL it's very difficult to do. And another important thing I wanted to add, this is my last slide, we were the first in the world to create multi-agent basic behavioral model. We showed that it turns out you can collect data in a special way, tokenize them and organize them for transformer training in a way that helps us identify the strategy or the behavior of an agent that factors in the behavior of other agents. It's very important. This article was accepted for AAAI, a very important international conference, and in navigational problems in multi-agent systems, I think this is a breakthrough. In conclusion, foundational behavioral models in robotics are very different from the models that we use for other problems, including multimodal agents. We need to make adjustments because our models need to work with data in a more efficient fashion, and they need to take into account the context that robotics provides. They are multimodal and multi-agent, even when we're talking about just one robot. This is something that we need. We do not need end-to-end architectures, and they are multi-agent in terms of interaction between multiple robots and humans. I agree with the previous speakers. I think that very soon we will have more fascinating videos showing that robots are not doing something in a standalone way, but are communicating actively with human beings, performing complex tasks. Thank you very much. Check us out on Telegram. We have a Telegram channel. We are just 90 subscribers short, I think, so do join us. Thank you. Alexander Panov, thank you very much for such an interesting presentation, and congratulations on what you said about your article, and congratulations on defending your doctoral thesis. As far as I know, that happened very recently. Congratulations. We have a couple of questions for you. Well, one question from the audience. You partially answered it, but apparently our audience, online and offline, would like you to talk a bit more about it. The development of robotics can radically change the world and our lives. What do you think are some of the other challenges that society can face now and in the near future? You partially answered that, but could you elaborate? When we are creating such powerful tools that disrupt our lives, multimodal models and language assistants, we need to add to this toolkit some educational component. We need to train people to use these tools and perform some frequent tasks so that people didn't view this as some magic. There's a magical fairy in my smartphone generating images. We need to bust this myth, and then there will be less fear of this technology. So I think technology plus education, that's the way to go. Thank you very much, Alexander Panov.